So in our last video about capacitors, we're going to look at charging and discharging a capacitor. Now this is where exponential functions and the use of logarithms comes in, and a lot of people don't like using logs. They are actually really useful, and hopefully by the end of this video you'll have a better idea of what to do when working with logarithms in capacitor equations. So let's imagine that we're wanting to charge this capacitor in the middle up. Now this here is an example of a charge-discharge circuit. At the moment it's set to discharge. If we flip this switch back to this side, we complete the circuit with the battery in, so we would be able to build up our differential charge over our capacitor. Now initially you don't have an overall charge on your capacitor, so it's quite easy to add charge. But over time, as the charge on the capacitor builds up and you're trying to force like charge onto an already densely packed charge distribution, you're going to get pretty large repulsive forces. And this means that over time it gets steadily harder and harder to deposit more charge on the capacitor. So we start off with a rather quick charge, and then as time goes on, the rate of our charging of the capacitor is going to drop. So our graph is going to look like this. But what about if we discharge a capacitor? Well, this time we've got the situation in reverse. Initially, we have a large amount of like charges on the capacitor. And this means that we'll get a very quick rate of discharge in the beginning. So if we're starting from our maximum charge here at the top, just at the instant that the circuit is switched to the discharge circuit, then we're going to get a very, very quick decrease in the amount of charge over a very small period of time. The rate of discharge is going to be very large. As time goes on, however, charge has leaked off the plate, it's been discharged, and so now the number of repelling charges has dropped. And so the repulsive force goes down, and as a result the rate of discharge is going to go down. And so we get a graph that shows an exponential decrease, a very quick initial rate that starts to slow and slow and slow and slow. Now in real life our capacitor will eventually lose all of its charge. In a purely theoretical situation, that capacitor is going to get continually and continually closer to zero, but never quite actually get there. Now the interesting thing about this being an exponential function is if we discharge a capacitor, we find that the charge decreases by the same fraction for each time interval. That is, if it takes 3 seconds to drop to a half of its initial, then in the next 3 seconds it will drop to a quarter to half of a half. And after 9 seconds, or after 3 lots of 3 seconds, it'll drop to an eighth to a half of that quarter, and so on and so forth. Now this means that we can start to do some nice working out of what is happening. And this whole process is called exponential decay, where the rate of the decay depends on the number of things that are decaying remaining. So if we imagine that we have a capacitor that's fully charged with a charge of Q0, if it discharges for 1 second, it drops down to 80% or 0.8 of Q0. What would its charge be after 2 seconds? Well, if in 1 second it's gone down by 0.8 of Q0, in 2 seconds it'll go down by 0.8 times 0.8, or 2 lots of 0.8 timesing each other. And so it would go down to 0.64 of its initial charge. What about after 5 seconds? Well, this time we'd have 0.8 times 0.8 times 0.8 times 0.8 times 0.8. And when we type that in, we get that it would drop to 0.33 of the original charge, or to 33%. And this, as we'll see later on, is very useful when we're looking at doing approximations. Now, the graph can be described by a very special relationship. And we know it's going to be an exponential graph, so we get the exponential function Q, so our charge at a particular time here that we're setting, is equal to the original charge, Q naught, e to the power of minus t, that's how long it's been discharging for, divided by the resistance of the resistor in the circuit and the capacitance of the capacitor. E is just an exponential number. You don't need to remember it. You can just press the E button in your calculator, which I'll show you later. But this gives us this lovely little graph here. And you'll see that the level at 37% is marked on, corresponding to the resistance times the capacitance, or RC. And that's what we call the time constant, and we denote that by a little tau. Now, the time constant is the time it takes for a capacitor to discharge to 1 over E of its original charge. That is about 37%, or 0.37 times the original amount. And that's very useful because it gives us a way, when we have a graph of charge against time, or, as we'll see later, voltage against time, or current against time, because it's an exponential decay, if you're asked to work out what the time constant, what RC is, just read off where 37% is on your graph, read across, read down, and where it crosses the x-axis is where your time constant RC is. Why are we so interested in 1 over E in this arbitrary time constant? Well, when we get to the point where the time that the capacitor has been discharging for is equal to the time constant, it's equal to R times C, we end up getting that our voltage is equal to V naught, original voltage, e to the minus 1, or 1 over E of the original voltage. And that's why it comes in useful. What about if you were asked to work out what the half-life was? Well, again, we're not going through the derivation because this is a quick revision video. If you want to, there are plenty of places that you can find the derivation for it. But it turns out that the time it takes for the charge, or the voltage, or the current to drop to a half of its original value is 0.693 times the time constant. And remember, the time constant is just the resistance of the resistor times the capacitance of your capacitor. And as I've mentioned so far, it turns out that we get the same relationship regardless of whether we're looking at charge, voltage, or current. They all have the same graph shape, that exponential decay with a very rapid rate of discharge to begin with that starts to level off. And they can all be calculated in exactly the same way. Okay, so let's have a quick look at a question then. A 5,000 microfarad capacitor is charged to a potential difference of 12.0 volts and discharged through a 2,000 ohm resistor. First question is, what is the time constant? Well, we know that the time constant is just the resistance of the resistor times the capacitance of our capacitor. Therefore, it is RC. And when I plug those numbers in, I get a time constant of 10 seconds. What's the voltage after 13 seconds? Well, this is where I have to bring in my exponential equation. V equals V naught E to the minus T over RC. I already know that RC is 10 seconds. I know that T is 13 seconds. So the voltage after 13 seconds is my initial voltage of 12 volts times E, and to get E, I just press Shift and then this ln button, the natural logarithm button, to get e to the x. So on most calculators, Shift and ln will give you e to the x, and then you can type in your x, which in this case here is the minus 13 divided by 10, plug that in, and I end up getting a voltage of 0.273 times my initial voltage, which is 3.3 volts. What would be the half-life of the decay? Well, remember we looked earlier that the half-life is 0.693 times the time constant, RC. Well, I worked out the time constant earlier as 10 seconds, so my half-life is 0.693 times the time constant, which gives me 6.93 seconds. How long would it take the capacitor to discharge to 2 volts? Well, now I'm looking to get a voltage there, and I'm looking for that time. So now the thing that I'm looking for is actually part of the exponential function. This means I'm going to need to take logs, and this means I'm going to need to go to the next slide to explain what we're doing. If we want to find t, if we want to find anything that's part of that exponential, we need to take natural logs, and that is again this ln button, but this time without pressing Shift. Now I know that V is V naught e to the minus t over RC. I know the V I'm looking for is 2 volts. My initial, if we look at the last slide, is 12 volts. And my resistance is 2000 ohms. So, this I know, it's my 10 seconds, my time constant, that I'm looking for, so I need to start rearranging this. First of all, let's get V's on this side. V divided by V naught equals e to the minus t over RC. Now, in order to get rid of this this exponential function, I need to take the log of this both sides. So the ln of V over V naught is going to be equal to the ln of minus t over RC, to the natural logarithm. And when I do that, I get that log V minus log V naught is equal to t over RC. Taking the log of an exponential makes it disappear and brings the power down. And why are we subtracting those there? Well, when you divide two numbers, you subtract their logarithms. Now that I have this here, I can just use my natural log button and do log of my voltage, that was my 2 volts, minus the log of initial voltage, my 12, is equal to the t that I'm looking for over RC. One last bit of rearranging, and I can plug all of my numbers in to get a time of 17.9 seconds. Now, it's really worth, if you're not used to it, having a practice with this natural logarithm button that we have here. If you're ever in doubt of which of these to use, remember we're using an e to the x function, so you need to use your corresponding logarithmic button. A couple of interesting facts about this charge time discharge graph that you get for a discharging capacitor. And remember, it's the same shape regardless of whether it's charge time, voltage time, or current time. But the shape isn't affected by the voltage. The half-life of the decay is independent of the voltage. So they're both set on the time constant of the system. Another thing you need to know is that to increase the time taken for a discharge, we can increase the resistance, which if you think about it makes sense. Increase the resistance, it's harder for the charge to be able to get through and flow out of the capacitor. Or we can increase the capacitor. Increasing either of these, think about what our time constant is. Time is RC. We can see that the time it takes for the capacitor to discharge to 1 over E will increase by increasing either of resistance or the capacitance. So, final example. A 50 microfarad capacitor is charged by a 6-volt battery, then discharged through a 100 kiloohm resistor. Calculate the charge stored in the capacitor before discharge. Well, I need to go back to using Q equals CV, plug my numbers for capacitance and voltage in, and I get a charge of 3.0 times 10 to the minus 5 coulombs. What's the time constant? Well, time constant tau is just the resistance times the capacitance, RC. So I've got my resistance of 100 kiloohms times my capacitance of 50 microfarads, and that gives me a time constant of 5 seconds. Now we need to estimate how long it would take to discharge to about 2 volts. Now, when you're given a question like this that is estimate, then it usually means you don't need to do the full equation, you just need to figure out what they're wanting you to do. So in this case, we know that the time constant is the time it takes for the voltage to drop to 0.37 of the initial voltage. Now the initial voltage here was 6 volts, and 0.37 or RC times 6 is 2.22, which is approximately 2 volts. So for an estimate question like this, first thing to check is the voltage or the current or the charge they want you to get to about 0.37 times the initial? If it is, then it's going to take the time constant RC to get there. Another typical estimate question is for you to work out what the resistance or the capacitance, but in this case we're looking at the resistance, the resistor would need to be for the voltage to drop to a certain amount. Now in this case, it wants you to estimate what the resistance would need to be for the voltage to drop to 99% less than the initial voltage. So it's dropping to 1% or 0.01. So we need to know how many stages of the time constant here, 0.37, it would take to get to that 5 seconds. Now as it happens here, in order to get to 0.01 or as close as you can in stages of your time constant here, you need 0.37 to the power of 5 or 0.37 times 0.37 times 0.37, etc. That gives you the closest possible value in stages of time constant to get to about a 99% loss of voltage. And the trick to figuring out this is how you do it is it's wanting you to work out one of the factors that you get in the time constant, either the resistance of the resistor or the capacitance of the capacitor. So now we know that we're going to have 5 incidences of the time constant RC in order to get our value of the voltage to be 1% of that it was in the beginning. So my time is going to be 5 lots of my time constant, so my time constant has to equal 1 second because my time is 5 seconds. Now that I know that RC is 1 second, I just rearrange 1 equals RC to give me R equals 1 over 50 times 10 to the minus 6, because that's my capacitance, and that gives me a resistance of 20,000 ohms. And that's pretty much it for capacitors. Have a go at the past paper questions, space engineers, and if you get stuck, drop me an email.